All right, so welcome. I'm Ryan Holger with TEC. This is part of a continuing series we've been doing on building automation related systems on Fridays. We did VAV last week, so hopefully many of you were able to attend that. We'll have a few references today back to last week, so hopefully that makes sense to anybody that was on last week, and I'll try not to lose anybody new this week. If you're watching the recorded version of this and you have not watched the VAV one yet, stop what you're doing, go back and watch VAV first. That will make more sense. It'll be more sequential that way. For those of you that need PDH hours for professional engineers in Illinois and Wisconsin, there's going to be, I think today, 5 questions that are going to pop up. You need to answer 3 of them correctly in order to be able to get credit. They're not very hard. You just got to be paying attention so you can answer them correctly. If you don't need PDHs, you're still welcome to answer it. No big deal there. GoToWebinar is going to automatically send you a thank you email later on tonight. There'll be a certificate attached to that, and that's fine. No problem with that. But the PDH certificate will come in a couple weeks after we grade all the quiz questions. And then Kelly from our office will send that out. So don't be alarmed when you get a certificate tonight that doesn't say PDHs. You will get one in a couple weeks that has the correct wording. We are way behind on the certificates because we've done so many online classes lately. All right, with that, I'm going to go ahead and jump into our topic. So today's topic, proper applications and sequences for constant volume pressure-dependent zoning systems. That is a huge long name. I probably should get rid of it and just call it VVT. But that's what I named it when I did this for the ASHRAE chapter like 15 plus years ago. And it's still the most accurate name, as you're going to see when life goes on here. But we all just call it VVT because it's just way easier, obviously. All right, so before we talk about VVT, we got to refresh a little bit on VAV just so you understand why VVT was even born. So VAV systems have been around for 50 years at this point. Very well-established type systems. They've done a very good job in mid and large size buildings, especially in office buildings. Main purposes for having a VAV system: get individual zone control for individual occupants. That's a primary driver. Save energy by slowing down a VFD. And back at that time, if you weren't doing VAV and you wanted comfort, you had to do constant volume reheat, which is a massive energy waster and not allowed by code. But VAV allowed you to save energy on that side of the equation as well. We can take advantage of building diversity. If your building needs, if your floor needs 60 tons of cooling, you could probably put in a 40 or 50 ton air handling system and get it done because not every zone needs max cooling at the same time. One really big catch, and I think I stressed it a lot last week, is that VAV systems are for buildings that want cooling year round. If your building doesn't need cooling year round, 365, you may want to double think about putting VAV in there. Specifically, the interior core zones needing cooling. The perimeter zones, okay, those guys are going to need heat in the winter in the Midwest. But the interior zones, if they don't need cooling year round, in other words, you don't have interior zones, your building's so tiny, there's no interior zones, then you probably shouldn't do VAV. A VAV system's normal sequence of operation would be to turn on in the morning on a schedule, open all the dampers wide open to 100% airflow, turn all stages of heating on in the rooftop or air handler, just blast the place and cook it until the return air temperature got up to like 68 or 70 degrees. Once that happened, the heat would be shut off. It would never come back on for the entire day no matter what, and the air handler would begin providing 55-degree cooling for the rest of the entire day. And then individual zones would have dampers that open and close to give you more or less of the 55-degree air. That would be a traditional VAV sequence. And you can see that on a big building that needs a lot of cooling, how that might make sense. On a small building that doesn't need cooling at all in the wintertime, it's going to be a problem. And you're probably not going to want to put a traditional VAV system on there. You're either going to want a modified VAV, or you're going to want to go to VVT, or a modified VVT. The two extremes have come much closer now in the past 10 years than they've ever been before. So what do we do in the small buildings? I can't put VAV in. It didn't make sense. I don't want to design it that way. It's going to be a problem. Got it. What can we do for a small building? Just everybody just gets the same airflow no matter what? No individual control? No, we have solutions. But the solutions that we have for those smaller units, typically rooftop units, 5, 10, 15, 20, 25 ton type equipment, meant that I didn't have a VFD. Well, back then I didn't have any VFDs, but I didn't have guide vanes available to me on small tonnage rooftop units, and I didn't have VFDs, and putting an air handler in would have been totally breaking the budget on some of these little tiny office buildings. So what am I supposed to do? Right? Additionally, VAV systems measure the airflow and static pressure at every single zone damper. I don't want to pay for all that. I'm probably in a budget constrained project if I'm using rooftop equipment, So I'm probably not going to want to pay for a bunch of extra sensing equipment either. And then on these small buildings, I don't have any interior zones. So I don't have any need for year-round cooling. So why the hell am I going to buy an air handler that provides 55-degree cooling year-round? Doesn't make sense. That's where VVT comes into play. VVT stands for variable volume and temperature. The variable volume part is because it's very similar to VAV, variable air volume system. The variable volume part is similar in that the individual zone dampers open and close their dampers, or they modulate them rather, to provide me less or more air into my individual space to take care of my individual load. So that the volume of air going into each zone varies, variable volume. The variable temperature comes into play to explain, the name was to explain that it was different than VAV. VAV is one temperature all day, no matter what, 55-degree air. VVT is typically 4 temperatures throughout the day. 2 stages of cooling, 2 stages of heating. Now you're going to say, oh, Ryan, last week you said VAV had to have like 4 or 6 stages of cooling. True, but those stages were controlled to give me precisely 55-degree air. VVT and constant volume rooftops in general, their 2 stages of cooling are not to provide 55-degree air. It's just one turns on, and whatever you get, say 62-degree air. The other one turns on, and whatever you get, say 57-degree air. There was no single temperature. So 2 temperatures for cooling, and then the same thing happens on the heating side. So that was the variable temperature part of the name. So variable volume and temperature. You're probably going to hear a lot of other names as well. This type of system has had so many names over the years, and there's probably another 5 names that I haven't even heard from some weird region of the country. But the ones I'm going to show you right now are ones that I've heard in the Chicagoland area multiple times over the years. Now, most people just call it VVT. It's just easy to say that. It sounds similar to VAV. VVT technically is a trademark term by Carrier. It's kind of like Kleenex. Maybe you say Kleenex instead of tissue, but technically Kleenex is a specific brand of tissue, right? So VVT is a specific brand of these zoning systems. So names you might hear, constant volume zoning. That name evolves because the air handling equipment provides a constant volume. It is 1 CFM. Now, as we start bastardizing these VVT systems, you're going to see that that's a little bit different. But traditionally and fundamentally, it's a constant volume air handler or a constant volume rooftop. In contrast to VAV, which would have had a VFD or inlet guide vanes that were changing the volume of air being delivered from the air handler. This is constant volume. So constant volume zoning is a common name you would possibly hear. Pressure dependent zoning. You might hear that. You probably won't hear it a lot because everybody gets really confused on what dependent and independent means. A VAV system is pressure independent. So what that means is that the individual VAV box has his airflow monitoring station at the inlet to the VAV box, and he's going to get his desired CFM for that moment, no matter what the air handler does. If the air handler provides more or less airflow, the damper will react and provide its damper position to be more or less to get the same amount of CFM that it wants. So if it wants 278 CFM, it's going to modulate to get 278 CFM independent of what the air handler is doing. A VVT system, in contrast, is pressure-dependent zoning, meaning it does not have the ability to measure airflow, it can't control airflow, it can't react and get the airflow that it wants, it just gets whatever it gets. So that damper is going to open up because it wants more or less cooling or heating, and it's going to get 150 CFM. And then maybe later on it gets 200 CFM when it does the exact same behavior. It doesn't know the difference. It just knows I want more or less. It doesn't know how much there actually is. So the zone is dependent upon the system pressure of the air handler. So we call it pressure-dependent zoning. Whatever the air handler is operating at, his pressure, determines how much CFM I'm going to get when I go to 50% open, for example. You might hear auto changeover VAV, right? So a regular VAV system would be cooling all the time, all day long, no matter what happens. Auto changeover VAV would mean that I've adapted my VAV system to be able to switch between heating and cooling. Auto changeover means that my thermostat can switch from heating to cooling. Well, in this case, the whole entire air handler system and network is going to be able to switch from heating to cooling. So you might hear that term as well. You may hear bypass VAV. That's a reference to the fan, VFD, and guide vanes that I was discussing. If you don't have guide vanes and you don't have a VFD, you had to have some way to control pressure, so you do it with a bypass damper, which I'll explain in detail here in a little bit. But some people have called it bypass VAV to mean a VVT style system. You might hear shutoff VAV. A normal VAV damper is going to operate between a minimum and a maximum CFM, and it's never going to go fully shut unless it's nighttime, for example. A VVT system, the damper is going to go fully shut. We'll talk about why that is and what penalties we have because of that. But a VVT damper is going to go all the way closed. So it might be called shut-off VAV. Obviously VVT. And then the last one you might hear, and you probably won't hear it very much unless you're talking to dudes that are old meaning older than me. So people that are in your 50s and 60s, those dudes might call it a Parker system, because this system was originally invented by a dude named Jeff Parker. He owned Parker Electronics, which Carrier eventually bought down the road. So it was Parker Electronics VVT system was the name of it. So sometimes we'll just call it a Parker system. You might hear that once in a while as well. If you guys have questions, type them in as we go. I see I got one from Mike. So Mike is saying, is pressure independent more popular than pressure dependent? As a general statement, if we want to go quantities of zone dampers in the industry, yes, there's more pressure independent zone dampers in the industry, meaning VAV systems. If you want to go quantities of buildings, it's probably more pressure dependent out there, because usually a VAV system will have 80, 100, 120 zones or something like that, whereas a VVT system, a pressure dependent system, will have 4, 5, 6 zones on it. There's tons of little buildings out there, not to mention everybody's house that has a zoning system is a VVT system. It's a pressure dependent zoning system. So the popularity would be based on whether you're asking on how many dampers are sold in the market or how many systems are installed in the market. Interesting question there, Mike. All right, so general application. We're going to put several zones on one air handler or one rooftop. Usually it's going to be a rooftop unit. Most of these jobs are, but it doesn't have to be. I'd say maybe 65, 70% of the VVT jobs that I've worked on over the years are rooftops, and then the rest would be air handlers or very large fan coil systems. Not very large systems, but very large for a fan coil. The zones themselves are going to be fairly small to medium size. But what the hell is small to medium size? We're basically talking about stuff that's at the low end, a really small zone, 100 CFM, and on the big end, probably up to 1,000 CFM. Could you have a zone with 1,500? Sure. Could you have one with 2,000? Sure. You could have some really, really big zones if you wanted to. At some point, you're probably doing it wrong. You're probably zoning it incorrectly. You're probably trying to save money on the project by combining zones into one big zone. If you got a zone with 2,500 CFM, it better be one really large open area. If it's individual offices and you're feeding 15 offices off of one damper, it's going to be a complaint job. So that's kind of why I have this 1,000 CFM check figure. I mean, that's 2.5 tons of cooling. That's already 3-4 zones grouped together in my mind. Most of these things should be pretty small if you're talking about like private offices at an office building. Most of the systems are going to have between 3 and 15 zones. Could you have one with 25? Sure. Could you have one with 2 zones? Sure. Could you have one with 1 zone? No, there's no reason to have one with 1 zone. Just don't buy any dampers at all, right? The average is between 4 and 6. It doesn't sound like a lot, but a lot of these things are going on little 10-ton rooftops, 12.5-ton rooftops, and that's kind of about how many zones you're going to have. Once you start getting above 15 zones, I start asking questions like, what kind of building is this? What's the layout? Like, why do you have so many zones? And when we do a layout here in a few minutes, you'll understand why if there's 20-some zones on one rooftop, why I'm going to raise the red flag. Because it probably means you're doing something you shouldn't. You're probably trying to mix an interior zone with a perimeter zone, and that's a huge, massive no-no. Or you're trying to mix the east zones with the west zones, another massive no-no. You can't do that. We'll do some compromises here in a few minutes when we lay a building out, but we can't do anything that extreme. If you mix an interior zone that needs cooling all year long with a perimeter zone that needs heating, I would 100% promise you you're going to have nothing but callbacks. It'll be endless. It'll be brutal. And one of the reasons why VVT has gotten a bad rap by some designers over the years. So try to keep that in your head. 6, 8, 10, 15 zones are the kind of normal range there. From an air handling or rooftop scenario, once people start getting above 20 tons, I also start raising a red flag. Like, what are you doing? Why do you have such a big air handler that has VVT on it? At some point, isn't this building big enough to be a VAV building? What are you doing? So I'll start asking questions like that. You shouldn't make the assumption that VVT is going to be less expensive than VAV. From a zoning standpoint, it's pretty much the same cost. You're buying dampers, you're buying controllers, you're buying sensors. Yeah, the VAV has the CFM static pressure inlet sensor as well. But other than that one widget, the controls is pretty much the same cost. The air handlers, if you do it right, you're going to have 4 or 5 rooftops on a building versus one big VAV air handler on a building. And it's probably going to be a wash there for cost. If you do it wrong, one really big constant volume rooftop, yeah, your equipment will cost less, but you're gonna eat it later in terms of callbacks. So once you start getting above 20 zones, I know I have on here 25 tons. Once you get above about 20 tons, I'm probably going to raise a red flag and say, what are you doing, man? We got to look at your building. Something's probably not right here. And even now, that I used to say 25 tons when I made these slides 15 years ago, and now today I'm telling you 20. And if I went and talked to like Sal or one of those guys in my office, they're probably thinking once you start getting to like 15 tons, they're probably thinking like a mini VAV system, because that's possible now with some of the equipment that we have. But back when I made these slides, you couldn't get VAV under 25 tons. It wasn't a thing for rooftops. And then on a square footage basis, 30,000, 40,000 square feet max. Once you start getting bigger than that, you're going to be really hard pressed to convince me you don't have interior cooling only zones. At some point, the building is just so big. Unless you have a really, really long, skinny building for some reason, then maybe you can get more square footage without having interior cooling only zones. All right, we got our first quiz question. And once again, if you're doing the live version of this, and you need PDHs, then you have to answer the quiz questions. Everyone is welcome to answer if they like, though. All right, quiz question number 1. Which would likely be the worst application of a VVT style zoning system? Your choices are going to be A, a single family house, B, an office area at an elementary school, C, a multi-floor high-rise building, or D, a dentist office. Which one is going to give you the most fits if you try to put VVT on there? And while you guys are doing that, I'm going to look over here at the question window and see if any questions are arising. It looks like we don't have any new questions, but feel free to put them in. Looks about like 60% of you answered it, so I'll give it another 20 seconds or so for everybody to make a choice. Once again, if you need PDHs, you have to answer the questions. I keep saying that over and over because after every class, somebody's always like, well, I didn't know I had to do it. Well, then I can't send you a certificate. I guess I could lie and do it, but I'm not doing that. All right, I'm closing this thing in 5 seconds. Pick something. 3 seconds. 1 second. All right. 73% of you got the correct answer, which is you're probably not going to be putting VVT in a multi-floor high-rise building. We got a question here that came in from Chun asking how we could determine between a rooftop and an air handler. That's actually, on the surface, it's like, really, that's an easy question, Chun, but it's actually a really good question because those things get confused a lot. So, for starters, a rooftop unit is always going to be outside. It's always going to be installed outside. It'll never be physically inside the building. Now, it might be on the rooftop, and it usually is in our marketplace, but sometimes it's on the ground next to the building. And when it is, we still call it a rooftop. An air handler, 90% of the time, is going to be inside the building, physically, inside the enclosure of the building, in the attic space, above the ceiling cavity, in a mechanical room, something like that. However, sometimes an air handler gets put on the roof. Well, then why isn't it called a rooftop unit? I don't know. The manufacturer has it in their catalog as an air handler. It's normally an indoor thing, and you've asked them to build it to be outdoor rated, and they do that for you, and they still call it an air handler. But rooftops are generally referred to as packaged equipment, meaning you could basically buy them out of a catalog, right? You can pick your options and order it, right? Whereas an air handler is something that's usually more built to order. It's more customizable. I can pick what kind of coils I want and things like that. But there is a lot of blur between the two. All right, let's keep moving here. All right, so let me get a little laser pointer. All right, so here's a rooftop unit. In this case, it's actually on the roof. Here's my return air coming back. Here's my supply air going out. It's in the cooling mode at the moment based on my very cool coloring of orange and blue. So my cooling air is coming out. I have 4 zones, 1, 2, 3, 4. Each one has its own thermostat. Each thermostat is wired to a zone damper. So it already sounds kind of similar to VAV, right? And those thermostats are telling those dampers to provide me more or less air. This guy wants a little bit of cooling. This guy's wide open. He wants a lot of cooling. This guy wants no cooling, so he's basically shut off. This guy actually wants heat, and he happens to have a reheat coil, so he's throttled back to some low airflow, and then he's reheating in there. The damper you see up here We did not have that on the VAV system last week. That's different. We have that on here because as these zones start to throttle their dampers back, the static pressure is going to be building up in this duct system. And when that static pressure builds up, I got to do something about it. Well, I don't have a VFD to slow down. I don't have inlet guide vanes to choke back. So I got to bypass the air and just dump it. In this case, I have a sealing plenum return. So I dump some of the air into the plenum and eventually works its way around and gets back into the return somehow. That's what I'm going to do to relieve the pressure in this situation. If at some point in time, maybe let's say this guy gets satisfied, so he closes off, he no longer wants cooling, and this guy starts getting satisfied, and then maybe this guy starts wanting heating. Once we have more zones that want heat than cool, after a time delay to protect the equipment, we will switch over and run this rooftop unit or air handler in the heating mode. And now we'll be providing warm air down the duct system, which means zones that want heat, like this guy, are going to open up, and zones that want cooling are going to have to temporarily shut off. Mike asks, what's the best way to figure out static pressure set point for the duct system? All right, so that's a good question as well. And depending on who I am in this scenario, makes a different answer. My role has typically been the guy that's setting the system up. I'm the guy out there programming the controls historically. At least that's what my job was in the 90s and early 2000s. So I didn't get to pick any equipment. I didn't get to decide how big it was. None of that stuff. I didn't size the ductwork. It just is what it is. So what I would do in those cases is I would be opening up my zone dampers when the air balancer is at the site with me. And granted, this is assuming someone hired an air balancer, which only happened like 60% of the time. And I have the air balancer hooding these guys to see if he's getting the airflow that he needs or not. And then I can back my system down on the static pressure set point to accommodate what he's seeing for the airflows on these guys. Very similar to what we do on a VAV system, at least traditionally on a VAV system. Now, for you guys that joined me last week, know that the code requires a specific set point of 1.2 inches on all VAV systems. But prior to that, we would set the static pressure set point on the VFD of a VAV with the air balancer's help. And we're going to do the same thing now on the VVT system. We're going to make sure we can get the air volume that we need to all of the zones and no more than that. There's no reason for me to do more than that. Now, on one side of the equation, you're going, so what if I over-pressurize the duct system? Who gives a crap, Ryan? It's not like the rooftop can slow down anyway and save me a bunch of energy. True, it can't, but in some cases, this duct might not be in a sealing plenum. And then when I have higher pressure, I'll actually have higher duct leakage, which means I'm leaking air into cavities of a building that are unconditioned for no reason, and that's pretty energy wasteful in itself. So I don't want to over-pressurize the duct system. I want to just provide enough pressure to get the airflow, in this example here, to this last zone on the end, zone number 4, because he's going to be the one that needs the most static pressure. In other jobs, it could be different. I might have zones that go left and right. I may have one with a weird duct system that has too many elbows off it, right? This guy right here might have had 17 elbows right here on zone 3. Okay, well now he's the worst zone instead of zone 4. But on this drawing, zone 4 is the worst. Let me spread out my question box so I can read the other questions. Okay. Mike asks if inlet guide vanes are against code. Gotta expand it more even. Foot on the gas and brake. I don't know if inlet guide vanes are specifically prohibited on code, but VFDs are required in most scenarios. As you saw before, anything above, where we at 65,000 BTUs of cooling up has to have a VFD on it. So at that point, you're not going to buy a VFD and guide vanes. So the guide vanes are essentially eliminated by the energy code requiring the VFD. So yes, essentially. Chun asked, out of curiosity, why is the supplier 55 degrees? Why no higher or lower than 55? It can be higher or lower. And if you do that, you just need to design the system for that. So for example, I live in Aurora, and there's a library over by me in Naperville on 95th Street. And that building, its entire VAV system was designed, I think it was either 45 or 47 degrees of cooling, which meant the chiller, instead of providing 45-degree water, has to provide like 39-degree water. The reason they did that was so they can make all the ducts smaller. If I can provide you colder air, I don't need as big of duct, right, to get the amount of BTUs to the space. I don't need as much CFM to get the amount of BTUs I want to the space. The two problems that occur in that scenario, though, are if you don't do a good job of diffuser selection and diffuser location, dumping 47-degree air on somebody's head is a little bit worse than dumping 55 or 56 on their head. The other problem, specifically at that job, is every time a new building engineer started working there, a couple months later, we had to go back out to the job and fix everything. Because they would go to the job and they would just automatically go change everything to 55. Like, why the hell is this set for 47? What the hell is this guy thinking? It's a waste of energy. And they put it at 55. The next week they'd be working on the chiller and be like, why you got it set for 39? And they'd set it back for 44. And they'd do it to keep fixing it because he was the new guy there and he made it like every other building he serviced. So it does become a challenge if you deviate from that kind of 55-degree rule. Most of the guys servicing your building won't realize that and they'll keep changing it back to 55 anyway on you. The other direction, if you want to go higher, the problem there becomes usually, unless you've done something specific with your coil selections, you're probably going to be too high of a wet bulb to really do any decent moisture removal. Once you start getting above 60 degrees on a normal feet per minute air handler, you're going to have a difficult time reaching the dew point and hence pulling moisture out of the air. So it ends up being that 55 to 57 degree dry bulb temperature ends up kind of being like a nice sweet spot. But you could absolutely design higher or lower than that if you do lots of other things different from industry standards. And sometimes things are done different. Let's see. Hardik says, suppose if all the rooms are in cooling mode, then the supplier temperature from the RT will be based on the minimum temperature required from each room. All right, so on the VVT system, we don't look at the supplier temperature at all. It's just going to be whatever happens, happens. So specifically, the way the supplier temperature is going to work. Let's just say I have all 4 of these zones. If 1 or 4 of these zones are calling, it doesn't even matter. And they're only calling a little bit, meaning that maybe my set point is 73 degrees cooling and it's 74 in the space. They only need 1 degree of improvement on there. They're going to ask this guy to turn on first stage of cooling. And then whatever discharge air temperature I get, which is probably going to be like 60 degrees. If any one of those zones asking for cooling gets warmer, let's say in this example, 2 degrees above set point, so it's 75 in the room on a 73-degree set point, then he's going to ask the rooftop to provide 2 stages of cooling. But I'm not going to be directly controlling the discharge, in which case I'll probably get 55-degree air. So I only got 2 stages to work with. The control system of the rooftop does not control the discharge air temperature. The space temperature of the zones controls how many of the 2 stages are on and whatever discharge temp you get. What you're thinking, Hardik, is more of a VAV style system where I have direct control of the discharge air. Now, with that being said, we are going to put a discharge air temperature sensor in this duct system. But we're going to use it as a limit protection, which I'll explain in a little bit. All right, let's keep on moving here. All right, so if I'm designing a VVT system, first thing I do is your load calcs. That's probably the true statement for every system. So no big deal there. Normally what we would do is do a block load first, which means I would do a load of the whole entire space as one big chunk, just to see what realm am I in. Am I in a 10-ton realm? Am I in a 50-ton realm? And then once I know that, I can get a gauge on what type of system I might want to choose. Then based on that, I can do some preliminary equipment selections. Rooftop, air handler, chilled water, DX, whatever I'm going to do. Get some basic guidelines on that regard. Then I'm going to determine which zones I'm going to put in. Do I need to have this zone separate from that zone? Can I combine these two? Should I separate these two? And we'll do that here in a minute. And then I'm going to do another load calc for the room-by-room load calcs. I'm going to need to do that at some point anyway, even on a non-VVT system, in order to figure out what size ducts go to each room. I don't need it to know my preliminary equipment selection because I just want to get something in the ballpark so I know if I'm starting to think about offering my clients rooftops or air handlers or some big massive chiller plant, right? But at some point I got to do room-by-room load calc so I can size the ductwork to the zones and figure out. The load will tell me, if I know the load of the zone and I know I'm going to use a 55-degree design temp, then I can calculate the CFM based on that, just like I would on a constant volume job. I'm going to determine where these diffusers are going to go physically in the space. It can be difficult. As a general rule of thumb for VVT or VAV, you don't want to put diffusers above places you think people are going to sit, because both of these kind of systems are at some point going to throttle their zone damper back, which means the diffuser is not going to get the kind of throw that it would at full CFM, which means the air is going to kind of dump. And if someone's sitting under there, like if you put a diffuser over a receptionist desk, you're just asking to get calls. You just know that you're going to get calls, right? And in individual private offices, you can pretty much guess where someone's usually going to put their desk. They're going to want a good view of the window, that kind of thing. You can kind of guess, and don't put the diffuser in those kind of spots, all right? So the position of the diffusers matters, and the selection of the diffuser matters. Just like last week on VAV, we said we want to have a diffuser that still has good throw, even at low turn down. And there are ratings for diffusers like that. If you're getting a Titus or a Kruger diffuser catalog, a GRD catalog, there's going to be ones that are even called like by name VAV diffusers. Those are the ones you want. Yes, they're going to cost more than the low-end diffuser. Yes, but that's the one you want to make sure no one gets dumped on their head and you get callbacks. Some people will tell you that you should be oversizing the diffusers to reduce noise. I'm not a fan of that. For VVT purposes, if you normally round up on all your sizes anyway for diffusers for all of your jobs, and you're having good luck with that, that's fine to do it on VVT as well. But don't do it because it's VVT. There's no reason to upsize because you think the VVT is going to be a problem. In cases where you have those noise issues on there, it's usually because that damper is the only one calling for cooling and all the other dampers are shut. And that only usually happens, what good grammar is that? That only typically happens when you've done a bad job of laying out your zones. If you've mixed interior and perimeter zones, yeah, then you're going to have a lot of times where one zone's calling for full cooling or heating and the other zones want nothing, and a lot of air is going to be rushing through his zone. Or it'll happen if you haven't set up your bypass or sized your bypass correctly. So normally I wouldn't go up in the sizes. I would just do my normal sizing on the diffuser as I would for any other system. I'm going to select my dampers. Typically what I do is I pick the damper to be around 900 to 1200 feet per minute. So I know the CFM, right, because the CFM came from the load calc, right? So I'm going to use my ductilator, the old sliding wheel, or some of you guys are using an app now, that's fine too. And I'm going to pick my CFM for that feet per minute range. So I'm going to go to 1,000 feet per minute and see what I got for my damper size in that regard. It is fairly common for the damper size to be a little bit smaller than the duct size, and I'm okay with that. In fact, I like it when the damper is smaller than the duct. Sometimes I will intentionally make the damper smaller than the duct. If I have a 12-inch duct coming in, I may on purpose put a 10-inch damper in. And I do the same thing on piping systems for control valves on air handlers. You may have a 2-inch water line coming to an air handler, and I may put 1.5-inch valve there. And you're like, dude, why'd you send me this 1.5-inch valve? Now I got to make a transition. Yeah, you got to make a transition. So what? Big deal. All right, I want to do that because I should have brought a graph of it. Valves and dampers have the same problem in that they don't have good controllability in the low range, meaning that once you get below 50% open, it's kind of sloppy. It's not very tight control, but by putting a smaller device in, smaller opening for that brief moment as I pass through the valve or the pipe or valve or the duct, I have better controllability of that. So I'll typically go smaller, which is why you see me using 900 to 1200 feet per minute on a zone damper. See if we got any other questions right now. Looks like we don't. All right, we'll continue on with these steps. Then I'm going to lay out the bypass system. I got some drawings. I'll show you that in a minute and figure out where I'm going to put the bypass and how big I'm going to make the bypass. I'm going to decide where I'm going to locate the thermostats. Same general good rules for that. Don't put them by doors. Don't put them by windows, that kind of thing. Obviously, each thermostat needs to be in the space that you're actually controlling with that damper. All right, goes without saying, I would think. In terms of the ductwork sizing, just like a constant volume system, I have to size both the main supply and return as well as the branches. And I'm going to start at the zones and work my way back. So you got your diffuser. You would size your ductwork going back to the main air handler. And then based on all your small branch ducts coming together, that determines your main duct size. No different than what you would do on a constant volume system in that regard. The main supply and return, let's assume I have one main supply and return going down a corridor and a bunch of zones branching off. That main supply and return is designed for the unit CFM. How much air is the air handler going to move? And obviously the branches are designed for the zone CFM. And as I take branches off, let's say I have 2,000 CFM coming down the duct for a 5-ton system. If I pull 300 CFM off, then after that takeoff, I obviously have my duct size for 1,700 CFM, and I keep transitioning it down, exactly like you would do on a constant volume system. I may need to select some supplementary heaters, specifically if I decided to mix exposures or mix some interior and exterior. I'm going to have supplemental heat. I can do VVT jobs with no supplemental heat, but it requires me to be smarter about my zone layout. And then I'll go back and tweak my equipment selection from the earlier preliminary selection. It's very important not to oversize the equipment. All of you guys have been in enough of my classes and webinars to know that I hate oversized equipment in general. I really, really hate it on zoning systems because not only is it oversized if I had all the dampers wide open, which is a problem, but I'm never going to have all the dampers wide open. So it's really a big penalty to me. Most of the systems that I've seen, you're essentially disabling second stage equipment on most of the pieces of equipment because the equipment is so badly, grossly oversized. The equipment should be smaller than if I didn't put zoning in. If you were going to put 10 tons in on a constant volume scenario, it may be 8 tons when you put a VVT in. You should have smaller equipment than you otherwise would, because not every zone is going to want full cooling at the same time. And then I'm going to figure out how I'm going to run all my control wires around. I got to get wires from the stats to the dampers, and then typically from damper to damper for a communication network. And then I got to get wires up to the air handling unit on the roof as well. All right, question number 2. All right, true or false? A rooftop with VVT dampers can simultaneously provide heating and cooling. Looks like my question got cut off. I'm too many words I put on there. So heating and cooling is what it would have said. All right, let's see if we have any other questions pop up. We don't have any yet. Now, less choices here, so you guys should be able to answer this one quickly. Looks like 57% of you already answered, so we'll give it another 10 seconds. All right, I'm going to close it down in 3 seconds. Pick something. 1 second. All right, the correct answer is false. The rooftop unit, in fact, no normal rooftop units can do both simultaneous heating and cooling. It can only do one or the other at any given moment in time. It looks like majority of you, 76%, got that correct. All right, moving on. Hang on, click there. All right, so here's the layout. This is basically the same layout I showed you guys for VAV last week because I'm lazy and I use the same drawing. This is a small office building attached to some kind of manufacturing or warehousing facility over here on the top end on the north side. In this particular case, we decided to put 2 VVT systems in here. If you recall, when we had the same exact floor plan layout with VAV, we did it with 1. Now, in the perfect world, I would have 1 rooftop unit for the west exposure, another one for the east, another one for the south, and 1 for the core. And then if there was no side building here, I'd have 1 for the north side as well. I'd have 5 rooftops on here. No one's going to pay to do that. So this is already a compromise decision here. So we have, in this case, we have 1 that is serving the south zones. So the main south zone plus the 2 corners. And then we have another system that is serving the interior core, the east, and the west. I'm not super excited about this at all. I would never have signed off on this, but this is what happens in real life. I don't want east and west mixed together at all. And I don't want interior and perimeter mixed together at all. It's going to be a problem. Interior, these guys over here always want cooling. But when this guy wants heating on the outside, I can't do both. I can't do heating and cooling. Can't do it. So the only way that I would ever sign off on this, and in this case do, is because these perimeter zones have these little red boxes, which means we added heaters to them. Same thing down here. Any perimeter zone add a heater on it. The interior zones don't need heaters because they're interior zones. They don't ever need heat. So what this allows us to do is that if these interior zones want cooling, we can run the air handling system in cooling. And if one of these zones calls for heat, we can throttle his damper back to some minimum position and then turn on his auxiliary heater. And now I can handle simultaneous heating and cooling. My air handler, my rooftop can't do it, but I could do it by adding, in this case, 3 heaters here on the perimeters. Now, if these guys didn't want very much cooling or didn't want cooling at all, they were satisfied at the moment, then I could run the gas heat on the rooftop and turn off these supplemental heaters and let this guy take care of the heat. Let's keep on moving here. All right, the bypass. We have to have the bypass in there because we don't typically have any way to slow the fan down. So we have to have a bypass to relieve my pressure. As zone throttle back, I got to do something with all this extra air. I'm going to dump it through the bypass. When I size the bypass, technically what I should be doing is look at the total CFM of the rooftop or air handler and then subtract off the smallest zone, because the worst case scenario is I have a 10-ton rooftop unit and the smallest zone is 1 ton. That means 9 tons of airflow would have to get bypassed. That's the worst case scenario. It's probably hardly ever going to happen because, like, why do you only have 1 zone calling for anything? That's kind of crazy, but it could happen. So that's how we typically would size the bypass. And then some other people will have other rules of thumb. I don't subscribe to this one, but some of them will size it for like 75 or 80% of the unit. I typically do this bypass calculation on the first line here. Then I select my bypass damper for 1,500 feet per minute. Now for the zones, I told you 900 or 1,000 or 1,200. The bypass I size with a larger feet per minute, which gets me a smaller zone damper size, because I'm banking on the fact that this scenario up here is hardly ever going to happen. Right? If it does, that's okay. My damper can still move the air. It'll just be louder. For that one moment in time when one zone's calling for cooling and 9 zones are shut, I'll have a little bit louder airflow noise, and I'm okay with that. And then once I've done this calculation, then I round my damper size down. So if it tells me, I'll just keep things simple. I'll keep it in round sizes for right now. If it says that I need a 14-inch round, I'm going to put a 12-inch in. That's my kind of personal rule of thumb, and that's based on my experience of seeing these dampers hardly ever open more than 25% anyway. Like, if it opens all the way, probably something else is wrong. They barely ever have to open all the way if you've laid out the system correctly. So usually I'll round down on the bypass size. We have to pay attention on the bypass to avoid short circuiting. If I'm going to take the supply air and I'm going to dump it back directly into the return air, that supply air has been cooled down to, say, 55 degrees. If I dump it right back into the return, that's going to be a problem because now my supply air is going to be 53 degrees. And then I'm going to do it again. And now it's going to be 50 degrees. And it's going to eventually cause me an issue. Same thing on the heating side. So I need to have some pretty good mixing. If I have a plenum return, it's awesome in terms of controlling this because I can dump that, let's say, cooling cold air bypassed into the plenum and it has to mix with all the warm plenum air before it goes back to the return air. Now, that's not awesome from an energy standpoint, but it's awesome for keeping this unit online, not causing me to trip out because I have too cold of return air. And the same thing on the heating side. So a plenum return is pretty favorable in that regard. If I'm not going to have a plenum return, I'm going to have a ducted return, then I have to do a good job of keeping the bypass as far away from the rooftop as I can get away with. And I'll show you how to do that on the drawing here. VFDs have historically only, I should add that word on these slides, have historically only been acceptable if the air handler has hydronic heating and cooling. And the reason for that was I can modulate those things as low as I want, heating and cooling valves as low as I want, and not have a minimum airflow that I need to keep the unit online. With DX compression or gas heat, that's significantly more difficult to do. With that being said, some of these rooftops are now available with a VFD on a VVT style system, and I can have some minimum limits put in there. You're probably still going to have a bypass damper with the VFD in order to keep these units online when I have small zones calling without everybody calling. Because I'm only going to be able to throttle that VFD down so far in order to keep this unit online, unless I get one with lots and lots of stages, i.e. a VAV style unit, which at that point, why isn't it a VAV project? This just, well, here, I'll show you bigger drawings of it. So this is showing you a plenum return style. So here's my rooftop. Here's my supply air going down the duct. It goes to all of his zones, does his thing, and then the return air comes back from all the zones through the ceiling grid, and then I have a little bit of duct work on there. When I open up this bypass to relieve the pressure problem, it's going to dump the hot or cold air into this plenum cavity, which is going to mix around until eventually it gets over back here to the return side. My static pressure sensor for VVT systems typically goes, well, it has to go downstream of the bypass. It cannot go upstream of the bypass because it needs to feel the effect of what the bypass did. So it has to go downstream of the bypass, and typically we're going to locate it before the first zone takeoff. On VAV style systems, we are locating it 2/3 down the duct or further in some cases. But on VVT, we're putting it a lot closer. We don't have the ability to react with that damper like we do with the VFD. But this is historically where this thing is going to get mounted here. If I have a ducted return, I want you to really, really, really try to not put the damper right here. It's super easy to want to do that. It's inexpensive to do that. It doesn't take up any extra space to do that. Everybody wants to do that, but it's the most likely cause of short cycling on the unit. The cold air comes out. If I have too much, it bypasses back into the return, and then my unit trips off pretty quickly. So in this case, I want to have some length here. The rule of thumb we used to say is you wanted to be at least 15 feet away from the unit before you had a crossover bypass duct back to the return. Most jobs never got that 15 feet. That was what we requested, but usually didn't get that. The further you get from the rooftop, the better it's going to be. The reason being is that means on the return side, I'm probably going to have more space to work with. This is really where the 15 feet is more important on the return side, because now my warm return, 78-degree air, and my cold supply, 55, have ample time to mix before they get back into the unit. They don't come through stratified like if they would if I did it right there. In some cases, I may need to put backdraft dampers on the return. It's not common, and it's not a requirement in all cases, But sometimes we need to do that because if I don't, and depending on which zones are open and not open, I could have air from this bypass dump down on somebody. So let's say there's a bunch of zones over here and those guys are all closed except for the very last guy who wants cooling. Well, the zones that are close to the air handler, they're not going to be open, so the room's not going to be pressurized, so the return duct's not going to be pushing air back into the return. So when this bypass opens, some of that air could go backwards into those close zones, and that could cause dumping on people's heads. It's not a normal thing that happens, but every once in a while it will. It's better to have the zones farther away if you can. I think some questions popped up. Chun says, where do you want to increase size for the return system before taking the return air or after in the return air to meet capacity requirements? I'm not sure what Chun means. From a duct sizing on the return and on the supply, there's nothing different we're doing on the sizing of the duct than we would do on a constant volume regular system. Typically, you're going to come off at a fairly large size, and as zones get taken off, which we're not showing on this drawing, as zones get taken off, you'll reduce your duct size. On the return, it's the opposite. The duct will be fatter here at the end, and it'll be skinnier at the beginning, if you will. And as more zones add into the return, it'll get wider and wider and wider. But no different than what you would do on a constant volume non-zone system. Tim says, would you place a zone duct connection between the bypass and the rooftop? I would not. I would not have a zone takeoff here if I can avoid it. If I do, that zone is not going to be benefited by my pressure control. It doesn't mean it couldn't exist. It doesn't mean it couldn't do a decent job of heating and cooling, but he's probably going to have a lot of scenarios where he's overpressurized because he's going to get whatever static pressure is coming out of this unit over here, if I took a takeoff here, versus a takeoff down here, he's going to get static pressure after some of that pressure has been relieved by the bypass. So I might end up with higher pressure and maybe more noise if I do that. So try to have your zone takeoffs down here after the pressure sensor. All right, let's see here. I mentioned the supplier temperature sensor for protection purposes. We will put a temperature sensor in the ductwork. And the reason we're going to do that is because as I'm throttling zones back and as I bypass more and more air, it's going to make my return air colder and colder in the summer, or in the winter, hotter and hotter. And when I do that, it's going to mean that I'm going to trip some limits in the unit, right? For example, a gas-fired rooftop unit is going to have a high limit switch on there, so I can't get above a certain temperature, whatever that thing is set for, 140 degrees or whatever it is, 150 degrees, something like that. I don't want that to trip off when my bypass bypasses too much air. And it is going to trip off for sure every single week, no matter what. It is going to happen on a VVT style system. So what I do is I put a discharge air sensor in the duct system so my VVT can be a early shut off, right? So he can sense that temperature, and let's say I set it for, here in this example here, I set it for 130 degrees. Maybe my rooftop has a limit of 150 switch in it. I set it for 130 in my duct system on the VVT, and if I get to 130, I'm going to back the stage off. I'm going to prematurely trip it with the control system before the mechanical safeties in the unit trip, because once those trip, they're going to trip so many times and they're going to lock out, and then there's going to be no heating and cooling at all. Same thing happens on the cooling side. So I have to put in these limits on here on my own so I can trip off the system with the controls before the unit itself would trip up naturally, because it will trip for sure if you don't do this. So on the cooling side, usually I recommend set points of 45 and 50. Once again, remember, I don't have any control of discharge air. Whatever happens, happens. So if only one or two small zones are calling for cooling and I have a stage of cooling on, it's very plausible that I'll get down below 45 degrees on the discharge air, and I'm going to have to kill that thing and stop it until such time as it warms back up, and then I can let it run again. So we're going to put those safeties in for sure. It's not very difficult to do. Actually, all constant volume control systems will do that. Even like ones for your house, if you get like a Honeywell zoning panel, they'll ship it to you with a leaving air temperature sensor for your house for that exact reason. The only one that doesn't do it is like an Infinity residential control system. It does it a different way, but that's a whole nother webinar. You need to put some guidelines in there on how the system's going to switch from heating to cooling and which mode it's going to pick. I can't have somebody asking for heat and somebody else asking for cooling. Well, I can have them asking. They just can't both get it. I also don't want my cooling to kick on because there's one small zone that serves the copy room or something ridiculous like that, or a thermostat that's next to the coffee pot. I can't have that turning the cooling on and off, hitting limit, off, on, limit, off, on. It'll beat everything up to death. So I got to have some minimum on there. Usually what I'll say is make it 25% of the zones have to call for cooling or heating before I turn on cooling or heating. So if you have 4 zones, 1 zone could call for heating or cooling. If you have 8 zones, I'm going to wait until 2 zones call before anybody gets anything, right? If you happen to have, 20 zones, then I'm waiting for 5 zones to call before you get anything. And that ensures that I don't beat this thing up by switching over from heating to cooling constantly. If you say, oh, it's not going to work for me, Ryan, because I have this one zone that just needs so much more cooling than the others. It's like a server room or it's a copy room. Guess what? That zone shouldn't be on the VVT system. That's going to be a red flag when you tell me that. Shouldn't be on there. Don't put a server room on a VVT system. It's always going to want cooling. It's always going to be a caller, and you can't give it cooling all the time. Usually we wait till all the zones satisfied before we clear the mode, and then we switch over to the other mode if need be, right? So we take care of the cooling callers. When they're done, we switch over to take care of the heating callers. Usually in the summer and winter, we don't have both, but in this spring and fall time, you do get some guys asking for different stuff based on sun exposure and time of year. We'll clear one mode before we switch to the other. Usually I'll put a 30-minute timer in there, and if after 30 minutes we still didn't solve all of the cooling guys' problems or all the heating guys' problems, whichever mode we were in, I'm going to go ahead and take a revote. Like, you know what? We had these 5 guys calling for cooling, and we had 2 guys calling for heat. I went to cooling. I tried to take care of you guys for half an hour. Let's vote again. And when I vote again, maybe it's 1 cooling caller left and 2 heating guys, and now I go to the heating mode. We can do some sequences to help out. Usually when the airflow is between certain temperatures, so I'll use the bypass to kind of make sure I don't get cold blasts of air for no reason. So I'll open the bypass damper until my duct temperature gets up to at least 65 in the heating mode. So I was in cooling mode, took care of those guys. I switched to heating mode. What I'm going to do in those cases is I'm going to shut off the cooling. I'm going to open up the bypass damper. And then when my air temperature gets back up to 65, because remember it was in the 50s from cooling, gets up to 65, then I'm going to go into regular mode where I control my dampers again, and I let my heat engage. And on the cooling side, opposite scenario, I'm going to wait until it gets below 80 degrees in the duct. So I was in heating mode. It was 100 degrees. I was heating the space. I satisfied the heat guys. I turned the heat off. I want to go to cooling. I'm not going to open my zone dampers when there's still lingering 100-degree air in there. I don't want to blast that in people's rooms that are begging me for cooling, and I'm going to blast 100-degree air in them. No. So I open up the bypass damper and let all of that 100-degree air cycle through the air handling system a few times until it gets down below 80 degrees, and then I'm going to let it go out and be delivered to the cooling zones that need it. Mike asks, is a 5-degree deadband still the minimum? That is the required deadband between heating and cooling set points for all systems per the International Energy Conservation Code. So not just VVT, but everything is supposed to have a 5-degree deadband between the heating and cooling settings. It does help out with VVT. If you try to keep things like really tight, like I want to be exactly 72 for heating and cooling. Well, guess what that means? It means your zone's always calling for something, either heating or cooling. You have a little bit of gap between there, and 5 is pretty good. Most buildings end up with a 2 or 3 degree gap. But 5 would be great if you could do that, Mike. I don't know that most people will function that way, but it'd be great. And then we'll have some limits on there for timers to make sure we don't switch over from a time standpoint too quickly. And usually the equipment nowadays has its own limits as well in that regard. From a ventilation standpoint, it's going to be very difficult for you to comply with ventilation code with a VVT style system. VAV, it's difficult. VVT, it's almost impossible. The reason being is if you've mixed zones that want both heating and cooling, you absolutely, positively, no matter what, have to let the dampers shut all the way down to 0% open in the occupied mode, which means you can't comply with ventilation code. But you cannot, at any point in time, let 100-degree air go into a zone that wants cooling. So when your system's in heating mode, if you got somebody that wants cooling, you have to shut the damper. If you don't do it, you will have a nightmare of a job that will never, ever, ever, ever have satisfied occupants. But Ryan, you're the code guy. You love complying with code. Yes, I'm telling you, you have to stop complying with the ventilation code if you want to have a VVT system that has zones that want heating and cooling at the same time. Or you could only put 1 air handler on the east, only put 1 on the west, only 1 on the south, only 1 in the core, only 1 in the north. And if you do that, then you should never have zones that want the opposite mode at the same time. If I have 5 private offices on the east side of the building, Some of them may want more or less cooling, but it's unlikely that one of them wants heat. And if they do, I can design it so they don't get their heat. That person's obviously unique. But I can do it that way. But if you start mixing east and west, there's always going to be people that want heating while others want cooling. If you want to start mixing interior and perimeter, somebody's always going to want heating while somebody else wants cooling. You have to let the damper shut all the way. I don't think I can say it enough times. Every single VVT job that I went back to that was a problem job almost always had this problem. Somebody put a minimum position on the damper. It will not work unless you've done an excellent job of zoning the air handlers. No minimum damper positions. I'm going to skip these ones in the interest of time just to keep things moving. Any kind of supplemental heat you could put on a VAV system, you can also put on VVT. So duct heaters, baseboard heaters, electric, hydronic, any of those things you can do. It all works exactly the same in that regard. And we'll talk more about that for you guys that are joining us in 2 weeks on the air handlers. Same thing with fan power boxes. I'll talk to you about those in a couple weeks when we do the air terminals, VAV air terminals. But you can use a fan power box on a VVT system if you want to. It is not common at all, but you can in fact do it, and there is ways to control it and make it work, and it would function very similar to what a VAV box would do. In fact, it would be a VAV box with VVT controls on it. You can throw all these things on the web. You guys have seen enough of our webinars and control systems and things to know how that works. If not, we have more of those coming up. Air balancing does need a little bit of discussion. So I can send this to anybody who wants this, but this is kind of the sequence of what needs to happen when you do the air balancing. Literally, I took this off of my cheat sheet from 20 years ago that I used to hand to the contractors and saying, give this to your air balancer. Tell him I'll meet him on the job site. We got to do this together. I don't have the equipment to measure stuff. He doesn't have the knowledge of how to manipulate the system. We got to go on the job at the same time. Give him this sheet, right? So this is the basic thing you would do. We'd open up command the bypass damper closed and open up all the zone dampers. Basically pretend it was a constant volume system. And then we would balance the airflow of the fan to the desired CFM like it was a constant volume system. And then we would adjust the maximum damper positions to provide the required design airflow to each zone. Right? There's no reason for a zone to be set up to take 500 CFM when it's only supposed to be taking 350. So we throttle those guys back, give them a maximum operating range on there. If you have fan power boxes, we would set those. We'll talk about that next week or 2 weeks as well. Then we'd set the duct static pressure set point for the bypass. Like I said, I'm trying to get air to the farthest zone. If I can get enough air there, I'm giving you too much static, I'll back my set point off until I'm not giving you too much static. If you have building static pressure control, which you seldom have on VVT, we could set that up as well, like we would on a VAV system. You set up the minimum position on the outside air damper the same way you would do it on a constant volume unit. No difference there. What else would we have to do on here? Most of these ones we would not apply in a normal VVT system. They're just on my cheat sheet in case needed. But I can send that to anybody who's designing one of these and needs a cheat sheet. All right, so let's do some quick rules of thumb here, and then I'll tell you a couple of things that have to happen on the current energy code if you want to use VVT. Right? And this is kind of stuff that I've already said, but we'll just kind of summarize it real quick. Don't put VVT on a system above 20 tons. If you do, call me. Let's talk about it. There's probably something weird going on here. Don't reduce the quantity of air handlers you would need because you're putting VVT on. If your job needs 5 rooftops, you put 5 rooftops on and you zone them further with VVT. Do not take it from 5 rooftops down to 2 because you think VVT is going to be some kind of cost saver. It is never a cost saver. It's a comfort desire. It does not save costs. It does not allow you to reduce the amount of rooftops or air handlers. If you do that, you're going to end up with the problem jobs, the whole interior and perimeter mixing and all of that stuff. Definitely do not oversize the equipment. It's worse than in any other scenario. VVT is the worst thing to have oversized air handlers on. Everybody's got a TXV now, so that's easy. Do not mix interior and perimeter. I think I've said like 7 times. Do not mix interior and perimeter. Do not mix east with west. Avoid that when you can. If you're forced to do it for some reason, make sure all the perimeter zones have supplemental heat. If you're forced to do it and no one will pay for supplemental heat, do not do the job. Walk away. It'll be a nightmare, I promise you. If you zone these things correctly, they work very, very well. But if you do it wrong, you'll be that guy that says, oh, I hate VVT, it sucks. Well, it doesn't suck. You didn't use it the way the manual said. Not you personally, somebody else. Don't put the bypass damper too close to the air handler. Don't put the bypass discharge near the return grills or you get that dumping effect. Do specify air balancing. Use that cheat sheet that I gave you. Make sure that air balancing is part of the project. It should be anyway, but I know sometimes things get value engineered out, and that's one of them. And definitely do not put a minimum damper position on any of these zones unless you've done an excellent job of not mixing perimeters and not mixing interior with perimeters. Then you can put some minimum damper positions in and follow your ventilation code. All right, quiz question number 3. When is it okay to mix interior zones with perimeter zones? I can't believe I wrote this question. All right, I'm only going to give you 30 seconds because this is an easy one. When the client requests it, if the project budget can't afford it, more multiple zones, if the controls guy says he can make it work, or if you install reheat on all the perimeter zones. Which one will give you a chance of surviving mixing the interior with perimeter? Okay, looks like we're mostly caught up on the questions here. 70% of you guys answered. Almost everybody got it right. I'm going to close it in 5 seconds. All right, I'm closing it now. Pick something. All right, awesome job. 97% of you got it correct. If you are going to force yourself to mix interior with perimeter, make sure all the perimeter guys got some reheat on them or you'll be screwed. All right, let me just show you what happens from the International Energy Conservation Code standpoint, and then I'll ask you one more question and then we'll be done. And I'll go through this quick because you guys already saw this on the VAV last week. All rooftops, all air handlers, all fan coils on the 2018 code that exceed 65,000 BTUs, which means they're more than 5 tons, have to have 2-speed fan control. That's automatic. If you're on the 2015 code, like Wisconsin guys are, that's not the case. But for Illinois, 2018 code, all your systems that are basically 6 tons and up have to have 2-speed fan control. Unless you have systems where the space temperature is controlled by modulating airflow to the space, i.e. zone dampers. If you have zone dampers, VVT, VAV, somebody else's brand of VVT, if you have that scenario, then you have to have modulating airflow control. So because of the new code, you actually have to have on your rooftop a VFD on your VVT system. And you still got to put the bypass in because the VFD probably can't back down far enough for your smallest zones. So you got to put a bypass in as well for when the VFD is throttled back as far as it can go to keep the equipment online, then the bypass can take care of the rest. If you don't do that, then what you have to do is put minimum damper positions on your zones, which, unless you've done a good job of laying it out, could be a problem. So keep that in mind. Make sure you're putting VFDs or some kind of modulating fan control, but I don't know why you would do something other than a VFD, on your VVT type projects. Staging, just like with VAV, same rules are going to apply in this regard. Because the rule doesn't say anything about VAV, it just talks about the number of stages required based on your capacities. So on a normal system with no zoning whatsoever, once you hit that 75,000 BTU mark, you're going to have 2 stages of compression. So 6.25 tons and up, you have to have 2 stages, all of your projects. Then if you have systems, once again, that control the space temperature by modulating airflow, i.e. zone damper systems, VVT, VAV, Honeywell, whatever, then you have to follow this table, which now if you have 65,000 BTUs and up, you need at least 3 stages. And if you get to 20 tons and up, you need 4 stages. And hot gas bypass does not count as a stage. So if you're going to put in, say, a 10-ton rooftop with VVT, you're going to need a modulating VFD fan, and you're going to need 3 stages of compression for a 10-ton rooftop, because 10 tons is 120,000 BTUs, so that's 3 stages. So you're going to have to do that on those VVT-style jobs. We saw this last week about how to throttle the dampers back. This whole entire section does not apply because it's specifically only for variable air volume systems. Now, technically, it says multiple zone systems, which would include VVT. So you're going to have to go ahead and do this, but it's not going to be a problem in real life for you because I already told you got to let those dampers go all the way closed. So you're already going to be below this percentage. So you're already going to be fine. So that's why I got the big X on that one. You don't have to think about it if you've done everything else I said. We don't have to do this one at all because it doesn't say multiple zone systems. It just says VAV systems. And we don't have a VAV system on a VVT. So I don't have to do the deal where I locate the static pressure sensor wherever it has to be for 1.2 inches of static. Not required by the code. If you're going to put fan power boxes in, that rule still would apply. You got to put an ECM motor in if it's a series fan power box. You don't have to do that if it's a parallel box. Supplier temperature reset. If you did a good job laying out the zones such that you don't need reheat, then you don't have to worry about this. You don't have to do it because you don't have any reheat, so this doesn't apply. You've already designed number 1 into the rules here, so you're good. However, if you've decided that you need reheat because you decided to mix perimeters or mix perimeter with interior and you have to add reheat coils now to make it work, then you're going to have to do some kind of supplier temperature reset routine on an air handler that doesn't have supplier temperature control. That's going to be difficult for you to do. So once again, my recommendation is make sure you put only 1 rooftop unit per perimeter. Do not mix them. Then you don't have to put reheat in, and you don't have to worry about these rules. All right, let's get these last 2 quiz questions right now so we can wrap you guys up. Which of the following would be required per IECC 2015 and 2018 on all 10-ton VAV systems? All. Variable speed fan control, 3 stages of compression, reheat, both variable speed and 3-stage, or all 3 of those things. On all 10-ton systems with VVT, which of those do you have to do? This will be the hardest question of the day. It's not that hard, but it's the hardest one. All right, half of you guys answered. I'm going to give you another 7 seconds. You notice my countdowns are very precise. Based on how many of you answered determines how many seconds I give you. Not that precise. I just make it up. All right, I'm closing it in 3 seconds. Pick something. All right, the correct answer, which most of you got correct, is in fact D. I have to have a variable speed fan because I'm above the 65,000 BTU threshold for that, for systems that control airflow with zone dampers. And I have to have the 3 stages of compression because I'm above 65,000 BTUs there as well. I don't have to have reheat at all. I may put reheat in, but I don't have to do it by code. In fact, the code prefers that I don't. All right, last question, and then we'll be done. No matter what you answer here, it's correct. You'll get credit for it. It's just it's the freebie to make the grading work out easy for me to make sure that you got 3 out of 5 correct. So answer whatever you want. I won't be mad. But if you answer 1 waste of time, then I will delete your PDH certificate. No, I'm just kidding. I won't do that. I'm getting in trouble there. All right, I'm going to close that one down. All right, and we are wrapped up. The only other thing I have for you, if you're interested in, this is part of several different webinars that we have done as part of this series or that we are still doing. If you're interested, and we also have some hands-on classes. We're finally able to have classes hands-on, live, in person in the classroom again. And we started we started Wednesday with our BACnet programming class. If you want to take that class, it's 7 weeks long, and Steve can get you caught up on that first week that you missed. So if you want to take it, you can still join us next week. Every Wednesday we meet for that class if you're interested. We have another webinar next Friday, HVAC integration basics and the future of building automation systems. And then the week after that, in 2 weeks, we have the VAV terminal units, basically part 2 of last week that I couldn't get in on because I talked too much. That's in there. We have another hands-on class for economizers coming up in July. And then for the guys that take level 1 of the BACnet class, there's a second level 2 for those that want to get really deep. And then on demand, we have a bunch of classes as well. And if you go to our website, go to the training page, you can search for any one of these things and watch those recorded webinars. So with that, I thank you guys for your time. I'm looking over here at the question box to see if there's anything else on it. I do not see any other questions popping up, so I'm assuming we're reasonably caught up here. So I'm going to go ahead and end the recording, and I thank you guys for your time.